So, all right, so let me just check if you guys are right in front of your computer. So again, just give me a thumbs up. Okay, so 4 out of 6. All right, so anyway, the other will just catch up to us. So this might only take a 5, let's say 10 minutes more or less. All right. So before I discuss everything, with the maximum power transfer theorem, okay. So before you can apply this one, okay, you must know the theorem, Thevenin's theorem, and then the Norton's theorems. Those two theorems, because if you don't know those two, you cannot. Yeah. Let's say, if you're not familiar with those two theorems, you won't be able to use this theorem at all. Okay, because the values of those, let's see, Thevenin's or Norton's theorem, those are the values that you're going to use for you to be able to solve the maximum power transfer that is being uh, transferred on that specific load or resistance. Okay, so yeah, that's actually it. Yun na yun. And then you only need to memorize one formula. Okay, but I will go on that one later on. Okay, just one formula and then you're done. Okay, so I could say that this is just an additional, okay, additional, let's say theorem or concept. Okay, that you can use in Thevenin's theorem and then Norton's theorem. But anyway, let me just read this one. So the maximum power transfer theorem is not so much a means of analysis as it is an aid to system design. Okay, this is not actually, another theorem wherein we can solve for individual resistances, individual currents, but this is just an aid to a certain theorem already, which is the Thevenin or Norton theorem. Okay, so simply stated, the maximum amount of power will be dissipated by a load resistance when that load resistance is equal to the Thevenin or Norton resistance of the network supplying the power. So if the load resistance is lower or higher than the Thevenin or Norton resistance of the source network, its dissipated power will be less than the maximum. Okay. So later on, we will discuss that one if we have a lower or higher, or if we have a 1:1 resistance with your RL. Okay. So this is essentially what is aimed for in radio transmitter design, where the antenna or transmission line impedance is matched to final power amplifier or impedance for maximum frequency power output. Meaning, if we have, let's say, a 1 volt that is coming from our source, then we should also receive a 1 volt on our, let's see, load resistance or our load. Okay, so that's basically the idea of maximum power transfer theorem. Because let's say if we have a 1 volt source and then we're only receiving, let's say 0.10 volt, then we are not maximizing the 1 volt that is coming from our source at all. So that would be, uh, let's say, unpractical. Okay, and it's not uh, how it should work. Okay, it should be 1:1 because we wanted to maximize the power that's being transmitted from our source. Okay, so impedance, the overall opposition to AC and DC current, is very similar to resistance and must be equal between source and load for the greatest amount of power to be transferred to the load. Okay, so having a small variation, see, if it's higher, then it will already degrade the power that will be transferred on our load. If it's lower, that's the same. It will also degrade the power that will be transferred to our load. Okay, so load impedance that is too high will result in low power output. Okay, I don't know how did this happen, because if we have a high voltage, let's say high load impedance, but as a result, we've got a lower output. Okay, but that's the computed values. That is why it should be a 1:1 only. Okay, having a higher is a no-no, and then having a lower is a no-no also. So it should be 1:1. Okay. So a load impedance that is too low will not only result in low power output, but possibly overheating of the amplifier due to the power dissipated in its internal or the Thevenin or Norton impedance. Okay, so later on, we will prove this one wherein we have a higher let's see resistance or lower resistance, which will lead us to a lower power output. Okay, so let's have this example. Okay, but this is already a computed result. So we have already applied, let's see, at the Thevenin's theorem, and then we've got a value of 0.8 for R Thevenin, and then 11.2 for E Thevenin, and then we have an R load of 0.8. So again, if you don't know how to come up with this kind of result, then you won't be able to apply maximum power transfer theorem at all. Okay, so you must master on how to get this kind of value first before you can jump in and then apply this maximum power transfer theorem. Okay, so the one that we are going to solve in here is where is it one? Anyway, so maximum power transfer theorem tells us that load resistance resulting in greatest power dissipation is equal in value to Thevenin resistance. So I think I wasn't able to mention the question, but the one that we are trying to solve is the uh, power, okay, that's being transferred to our R load. So we should be able to maximize, let's say, the power that's being dissipated from our E Thevenins, okay, that will be passed on our R load. So the one that will dictate the final value that will flow on our R load is the R Thevenin's value. So as you guys can see, they are the same. So if we have 0.8 on our R load, then it should match the value of our R Thevenin. So we should have a 0.8 also. So if you have 0.7 or 0.9, that's already a no-no. Okay, so there are some cases where circuits must be like that, wherein we have a matching resistance value that's being needed by our R load. Okay, so here are the computed results. Okay, when it comes to the individual voltages or voltage drops. So we have a voltage that is 5.6 that is flowing on our R Thevenin, and then 5.6 on our R load, which resulted in 11.2. So since they have the same resistance, so just divide that into two. Okay, ganun naman eh, parang voltage divider. So I think that's very obvious. So just divide this one into two, and then one half will go to R Thevenin, and then one half will go to R load. So that is why we have 5.6 and 5.6. And since they are in series, we have a single value of current, which is 7. Okay, so just apply Ohm's law. So you'll be able to get the value of current, which is 7. So I is equal to V divided by R. And then we have the individual resistance value, and then the total resistance, which is just the summation of your resistance since they are in series. And then we have here the computed power. Okay. So in here, you can just simply apply, okay, the P is equal to I times B, the formula that we have in power. Okay. So if we have or if you're trying to solve the power that is flowing on our R Thevenin, then you should get the individual current and then the individual voltage that is flowing on that specific component. So in here we have, so in here we have P is equal to IV. So I is 7 and then V is 5.6. So just multiply that one and then you will get 39.2 watts. Okay, so the same with our load. So 5.6 times 7 will give you 39.2. And then of course the total is 78.4. So you can use the total current and then the total voltage. Okay, so you can also apply I squared, oops, PIV. Tama ba? I is equal to V divided by R. Ito yung isang formula, E squared divided by R. So you can also use as 1 or BIR. Yeah, I squared times R. Okay, so any of those, you will get the same result. Okay, so Are we clear so far on how did we get those values?
Yes, sir. Clear naman po.
All right. So in here, you'll be needing the individual currents and then the individual resistance or individual voltages. So we have a shortcut for this one. It's just that I wasn't able to save, I guess. So nandito siya. Ito. So hindi ko lang nadagdag. I will just replace the PDF version later on. But just use this formula. Okay, P max is equal to 1/4 VTH squared divided by RTH. And then you will get the same result. So the main advantage of using this one is you won't be needing the value or the individual values for, let's see, the voltages or the current. As long as you know the VTH and then RTH, then you can already solve the Pmax on that uh, circuit. So let me just get this one and then place it right here. Okay, so we will use this formula and then Pmax is equal to 1/4 times VTH, which is the E-Thevenin. So it's 11.2 divided by, gulo na pala to. So let me just use the pen tool, yung brush na lang, hindi ko mailalagay sa baba. So Pmax is equal to 1/4 times VTH, which is 11.2 volts, and then squared divided by RTH, which is 0.8. So the Pmax that we are solving here is the power that will be transferred on our R load. Okay, so please solve this one. Try to use your calculator and then verify if we will get the same result, okay, as 39.2 watts, which is the same with the power that is flowing on our R load on this uh, result in here.
Gets naman, sir.
So is this correct? Were you guys able to verify?
Wait, sir. Calculator ko lang po.
Sir, na-verify ko na po.
Na-verify na. Okay, tama na. Tama naman.
Yes, sir.
Okay, great. So you can simply use these formulas, or the fastest way is by using this formula. Okay, Pmax is equal to 1/4 times VTH squared divided by RTH. So how about you, Mr. Carlo? So wait ko na lang kung tama rin ba yung makakompute mo.
Yes, sir. Tama naman po.
Okay. Alright. So in here, we have a computed value of 39.2. Okay, in which the resistance that we've used is 0.8. Okay. So ito yung pinaka sagad na wattage na makukuha na natin if we have a 1:1 value, okay, of our R Thevenin and then our R load. But if you're going to lessen that one, let's say 0.5, okay, it will give us a result of 37.11. And then if we have, let's say, a higher value, which is 1.1, it will give us a result of 38.22. Okay, so if you guys are going to compare this one, so ito yung higher, and then ito yung lower. And this is the exacto lang, 1:1. Okay, so we have here 1:1 value, so 0.8 value ng R Thevenin and then 0.18 yung R load natin. Okay, 1:1. And then in here, so hindi ko na alam yung ratio, pero mas mababa. Okay, so lesser value. Okay, so we have a lesser value of our R-Thevenin in here. Okay, which is, let's say, oops, my bad. Teka lang. Ang nabago pala. Well, anyway, either of those, okay, dapat matching sila. Kasi dito, we have a higher pala. Okay, we have a higher 0.8 R-Thevenin, okay, which resulted in 37.11 kasi yung R load na natin dito is 0.5. Okay, and then in here we have a lower or lesser value of your R-Thevenin kasi yung R load na natin is 1.1, okay, which resulted into a lower wattage also. So as you guys can see, the best value of your R-Thevenin and R load should be 1:1. So kung ano yung value ng R load, dapat same sa R-Thevenin. Kung ano yung value ng R-Thevenin, dapat the same sa R load. Kapag hindi sila magkaparehas, most likely you won't be able to get the maximum power transfer. Okay, so 39.2 is higher than 37.11, 39.2 is higher than 38.22. All right, so in here, the one that we are trying to prove in here is the efficiency of your circuit. Okay, so we must maximize everything that is coming from your voltage source just by tweaking the values of your resistors. Okay, so yun lang yung pinaka main goal ng maximum power transfer theorem. So were you guys able to get the idea so far? Hello, hello. Are you guys still around?
Yes, sir. Nandito pa po.
Okay, so this is the correct one, and then the other two is wrong. Okay, when it comes to maximizing the power transfer. Anyway, so if you were designing a circuit for maximum power dissipation at the load resistance, this theorem would be very useful. Okay, very, very useful. So lalo na kapag, let's say, gusto mong alamin kung ilan ba talaga yung kaya niyang yung parang sagad, okay, na kaya niyang i-deliver dun sa, let's say, sa device na yon, then maximum power transfer theorem is very, very helpful. Okay. So having reduced a network down to a Thevenin voltage and resistance or Norton current and resistance, you simply set the load resistance equal to that Thevenin or Norton equivalent or vice versa to ensure maximum power dissipation at the load. So practical applications of this might include radio transmitters. So ito, lalo na sa mga signals natin, so dapat 1:1 yung mga yan. So kung ano yung binabato mo, dapat yun yung ma-receive. Kasi kapag meron lang konting inaccuracy. So malaking bagay na yon para dun sa manakikinig. So kung merong konting noise, syempre masakit sa mata. Okay, ganun din kapag nasobrahan mo, hindi rin magiging maganda. So dapat saktong-sakto lang. Kaya kapag pumipihit tayo ng radyo, di ba? So merong tamang timpla, let's say 107.8, hindi ko alam kung yun ba yung tama. Pag naging 107.7, naririnig mo naman na yung nagsasalita or yung music coming from that radio, pero may background noise. Ganun din pag sumobra ka. Pag ginawa mo 107.9, okay, which supposedly 107.8, so sobra ka ulit, ganun din, meron ding background noise na maririnig. So dapat saktong-sakto. Okay? And a grid-tied inverter loading a solar array or electric vehicle design, so seeking to maximize the power delivered to drive a motor. Okay, and then more review or conclusion. So the maximum power transfer theorem does not coincide with maximum efficiency. Okay, so application of the maximum transfer theorem to AC power distribution will not result in maximum or even a high efficiency. So kung ano lang yung talaga yung sagad niya, then that's the 100 efficiency that you can already give. Okay, hindi siya yung parang amplifier na yung 1 mo is magiging, let's say 1:5. So let's say magiging mas maganda pa. So hindi ganun. Okay. So the goal of high efficiency is more important for AC power distribution, which dictates a relatively low generator impedance compared to the load impedance. Okay, so similar to AC power distribution, high fidelity audio amplifiers are designed for a relatively low output impedance and a relatively high speaker load impedance. So as a ratio, output impedance or load impedance is known as damping factor, typically in the range of 100 to 1000. Okay. So maximum power transfer does not coincide with the goal of the lowest noise. For example, the low-level radio frequency amplifier between the antenna and a radio receiver is often designed for the lowest possible noise. So this often requires a mismatch of the amplifier input impedance to the antenna as compared with that dictated by the maximum power transfer theorem. And then lastly, the maximum power transfer theorem states that the maximum amount of power will be dissipated by a load resistance if it's equal to the Thevenin or Norton resistance of the network supplying power. Okay, so dapat equal lang silang dalawa pareho. And then the maximum power transfer theorem does not satisfy the goal of maximum efficiency. So kagaya ng sinabi ko kanina, hindi ito yung tamang way para makuha mo kung 100% na ma-maximize mo talaga. Kasi hindi siya yung parang ano bang tawag dito? Amplifier. Okay, wherein, let's say, 1 magiging 5. So ito, 1:1 lang siya. Kung ano lang talaga yung kaya niyang ibigay using that circuit, and then yun na talaga yan. Okay? So in here, with the use of the maximum power transfer, you can just solve the power that you can transfer on that one. Okay? So here's the reference for this module. So this one came from All About Circuits, or you can also check this website if you need more explanations. Okay, so one is coming from electronics tutorials, and then the other one is coming from tutorials point. And then we have here sample videos. So we have 3 English videos and then 1 Tagalog videos. So make sure to visit them. Okay, and then that's it for the maximum power transfer theorem. So any questions so far or clarification?
Wala naman po, sir. Gets po.
Okay.
Answer.
So sa ngayon, what do you guys think is the hardest theorem, okay, when it comes to finals? So we have
Kirchhoff's pa rin, sir.
6 theorems in finals, starting from Thevenin's, Norton's, and then ano na yung dalawa? So we just discussed that one last meeting. The last 2, naglalag na. Okay, the last 2 is the source transformation, which is also easy, and then the delta to y, and then y to delta transformation. So what do you guys think? So sa inyo, so of course, Kirchhoff's pa rin, and then Maxwell maybe. But what about in finals?
Sir, nagets naman po lahat. Yung Kirchhoff's pa rin talaga.
Kirchhoff's pa rin. So yeah, I really think that Kirchhoff's and then Maxwell is also one of a tricky theorem. Okay, but once you guys have understood them, then parang okay na lahat actually. Kasi yung iba, most likely for given ng formulas, and then you're good to go. Anyway, so yeah, that's already it. And then I will not be giving a quiz anymore for the Millman's and then the maximum power transfer theorem. So just answer this last 2 quiz. Okay, the source transformation and then the delta to y and then y to delta transformation. Then after that, will be your final exam already. All right, so yeah, that's it. So if you guys don't have a question anymore, then just give me thumbs up, and then you guys, and then again, thank you guys for coming. Okay. And keep safe.
Thank you, sir.
Thank you, sir.
Bye, sir.
Goodbye.
Hi, sir.
Bye.
sir. Good luck po.